Okay, that should work. Okay, hello. Everybody read section 1.3? Yeah? Okay. Does anybody have any questions? Pretty easy. Thought I needed to talk about it today. Okay. I guess, where should we start? This section was about vectors. It's a very basic and concrete introduction to the more abstract version of this that we'll talk about later, which is vector spaces. The fundamental object that we talk about in linear algebra, a vector space, and functions on vector spaces that sort of preserve the structure. Okay. So, you've seen vectors before, you've heard this term before. Examples that you've seen before are lists of 2 or 3 real numbers. So for example, I think in Calc 3, the notation that we use is something like, let's do a list of 3 numbers. So that'll be our first example. We sometimes use angle brackets, sometimes use parentheses. It really doesn't matter. So this would be an example of a vector. 3 numbers, 1, 2, 3. And an example of another vector would be i.e. square root of 2. Just to drive home the fact that these are real numbers and not just integers. Even though usually, a lot of times we're writing stuff like this in this class. Just because it's easy, that's all. Okay. And there were a couple of things that we could do with these lists of numbers. One very important one is add them together. And so, addition for vectors, for these lists of numbers, just an ordered list of numbers, right? There's a first one, a second one, and a third one. Okay. The addition is just defined term by term. So we just add the first with the first. I can remember how to write. Second with the second. And third. Well, I wrote this one out of order. Actually, it doesn't matter, right? Because order doesn't matter in addition. And because of that, because we could swap each of these and still get the same thing, that means that the order of addition doesn't matter in vectors either, as a consequence of the order of addition not mattering in real numbers. So this would have been the same as i.e. square root of 2 plus 1, 2. So it has this nice property, commutative property. The other thing that we could do is we could take a vector. Let's use I'll continue right here. 1, 2, 3. And we could multiply it by a real number. Okay? We call that a scalar because we're scaling it. So what should I multiply this by? Let's multiply it by -1. So we had this, I'll draw a little dot here just to emphasize the fact that I'm multiplying. -1 times this, again, it's just component-wise. -1, -2, -3. So this is hopefully review, but maybe not. Okay. And there's a geometric. I don't need to write out the whole sentence. There's a geometric interpretation of these things. When I say geometric, I mean spatial, in terms of drawings. If we had a vector of two numbers, so it's a list of two numbers, we called it a two-dimensional vector without really giving much explanation as to why we call it two-dimensional, except that if we have the 2D plane, let me mark off some distances on here for the sake of convenience. Then a vector can be, a 2D vector could be interpreted as either a point in the plane, right? Because every point in this plane is defined by a first number and a second number. And the order matters, right? So the vector 1, 2 could be this point right here. So when we were just talking about a point, we usually use parentheses for that. That was the convention. So that's the point 1, 2. And we can think of, another point, 2, 1. Another one on there. 2, 1. Now when we're just talking about points in the plane, it kind of doesn't make any sense. What does it mean to add these things? That's kind of a strange notion, adding points together. However, there's another geometric interpretation, which is of arrows. I can try to draw arrows like this. Then these arrows, well, this is the arrow 2, 1. Now I'm using angle brackets to indicate that it's an arrow and not a point. 1, 2. There's an obvious translation between these two things. If you have a point, you can draw the arrow from the origin to that point. If you have an arrow, just draw the point at the tip of it and forget about the. Set this in at the origin and then drop the arrow and draw a point at the tip. Okay. I told myself the other day I'm going to try to stop saying okay after every sentence. I'm going to try hard. Not making any promises though. Okay. I need a break. Does anyone have any questions? This is all review, so I can understand if you wouldn't have any questions. It's just a vocalized pause, right? Yeah, I should get over it, but it's hard. So, the addition of these two vectors symbolically or algebraically is this, and component-wise we get 3 and 3. And geometrically we had an interpretation, well the vector should be this one, 3, 3. And if you recall, it's not going to be perfect anyway. If you recall, the way that we could get to this, to the arrow, so this is the arrow 3, 3, was to take one of these vectors and put it on the tip of the other. So if I take the end of this one and I put it here, I get to the same point. And if I took this one and I put it on here, again, I get to the same point. Pretend I drew everything to scale. And so that was the geometric interpretation. In terms of arrows, we could take an arrow and put another arrow end to end, and then draw the arrow from one end to the other. And that gave us the sum. So that's a nice geometric interpretation of what was just an algebraic or symbolic thing that sort of just came out of nowhere. What's the sum of these two things? You add the components. Why? I don't know, because I say so. Right? That's just the addition. Okay. It's a little deeper than that, but I didn't give any kind of explanation. Now this is a geometric interpretation. It kind of looks like it makes sense. This is something that you do with arrows. It also has the added benefit that if I take this arrow and I put it here, or take this arrow and put it here, it doesn't matter, and that corresponds to this commutative property where it doesn't matter which order I had them in, right? The addition doesn't matter. That's one of the reasons that we call this addition, is that it has this nice commutative property. You're probably used to multiplication having the commutative property too, so why didn't I call it multiplication? Any guesses? Nobody's read ahead. Later on, we talk about multiplication of matrices. So we have a multiplication that's defined like that. And we also have an addition of matrices. And with matrices, this multiplication that we define is not commutative. Actually, it will matter what order we multiply things in. We'll get different answers depending on the order. So that's sort of a theme throughout algebra, not just linear algebra, but other types of algebra as well. That we call multiplication the one that could possibly be not commutative, in addition to the one that is commutative. Okay. There it is again. Okay. I can't stop. All right. This one, the list of 2 and 3 numbers, we had special names for these. So R2 and R3. R, draw this. This is the real numbers. This symbol stands for the collection of all real numbers. So if we took every real number that's possible and threw it into a bag, this is the name of that bag. This is like a bag of money with a $sign on the outside. This is the bag of real numbers with the R on the outside. And this R2 really means, well, it's 2 copies of that bag. We pick something from the first one and we pick something from the second one. So this is all of these vectors, the list of 2 numbers. This is the symbol on the outside of that bag. This one is the one with the list of all lists of 3 real numbers. Well, there's an obvious generalization to this, which is Rn, and this is lists of n real numbers. So we pronounce this Rn, or let's just call it Rn. Just like we called this 2-dimensional and this 3-dimensional, we're going to call this n-dimensional, but I haven't really made it specific what I mean by n-dimensional space. 2 dimensions is kind of clear. You have a picture of this in your head. N-dimensional space, probably not. Okay. But the fact that we can just talk about this as lists of n numbers means that we can deal with these things. We can do computation with them, even though we can't draw pictures of arrows and put the arrows on the ends of each other. Any questions about that? So we had vector addition. Oh, I should probably put names of these. So these are our 2 operations. Vector addition and scalar multiplication. In 2 dimensions, we had another kind of, in 3 dimensions, we had another kind of multiplication. Does anybody remember that? We had a product. We did have a dot product, but it did not give us another vector. Yeah, cross product. We had the cross product in 3 dimensions. We have the dot product actually in any number of dimensions. It's easy to see how that works. But cross product actually only works in 3 dimensions and 3 and 7 dimensions. There's a cross product in 7 dimensions as well. But it's kind of unique to 3 dimensions. It's interesting because we live in 3-dimensional space, right? There's also a multiplication that we're not going to talk about either in 2 dimensions, and that's when we treat these 2-dimensional real vectors as complex numbers. So the first number is the real part, the second number is the imaginary part, and then we do complex multiplication with them. And that is also, in a sense, unique to 2 dimensions. There isn't something in higher number of dimensions that works quite as well. There are things in 4 dimensions and in 8 dimensions that work, but aren't quite as nice as in 2 dimensions. Okay. That was burning up. That was a quick review and the introduction of Rn. And now I'm going to enumerate some properties. We'll come back to these properties later, but I just want to say them really quickly. So, U and V vectors, so be very careful with your coughs. Remember, we're in the middle of a worldwide emergency. That doesn't mean we're going to stop doing math. Okay, so these are vectors in Rn, and C and D are real numbers. I surreptitiously switched to using more mathematical notation. This means that C and D are in something in this bag, right? Not necessarily distinct. They could be the same. Okay, the first property is that U plus V equals V plus U. That's what we talked about before, the commutative property. The second one, U plus V plus, let's do it in the same order as both. U plus V plus W equals U plus V plus W. This is again justified by the same property in real numbers, that it doesn't matter if I add the first 2 and then the third to that, or if I add the second and the third and then add the first to that. Doesn't matter. That's called associativity. The name's, well, that's the name. And that's what allows us, well, if I wrote U plus V plus W, without knowing that it doesn't matter what order we add them in, that might be ambiguous. So with this rule, we're saying it doesn't matter. Either way is the same. So we can talk about our arbitrarily long sums of vectors. Okay. So property 3, 0 plus V equals V plus 0 equals V. Where I didn't say what 0 is. Also I should say this. In the book, they signify vectors with a bold type, and scalars with a normal type. I can't do that on the board, and so oftentimes what people will do is that they will write arrows above everything that they intend to be vectors. I'm not going to insist on that convention because I don't use it in my daily life, in my daily math life. And so I'm not going to insist that you do that in this class. But if it makes things easier for you when you're writing stuff, feel free to do it. If it doesn't make it easier, feel free to not do it. Okay. 4. Equals U plus negative U equals negative U plus U equals 0. Okay, so everything has a negative. It's obvious how to get that. Just change all of the entries to negative of whatever they are. Switch them to the whatever. And what we mean by negative U, this is by definition. When we write negative U, what we really mean is negative 1 times U. 5. Here's where we get to the scalar properties. C times U plus V. We have the distributive property. It works in the way you would expect. The other distributive property, yep. So if you add the scalars first and then multiply by the vector, it's the same thing as multiplying the vector through and then adding. So that's the distributive property for the scalars as opposed to the vectors. There's the associative property of scalar multiplication, which is C times du equals C times D times U. So we can multiply the scalars first and multiply by the vector, or we can multiply them into the vector one at a time. Doesn't make any difference. And finally, there's a special scalar. It's very important to us. It's called 1. And of course, 1 times any vector does not change that vector. Are there any questions about these? And for convenience, U plus negative V, we simply write as U minus V. You're probably having the same, does anybody have any questions first of all? I didn't anticipate a lot of questions on this. When I first saw this, I thought, yeah, obviously, right? All of this stuff is really obvious because we know what the vectors are. The vectors are these lists of numbers. We know how addition works. We know how multiplication works. Okay, this is just saying all the things that we know about real numbers. We're just saying about vectors too, right? That's obvious. Okay, the problem is, what if the things that we're calling vectors are not just these lists of numbers? Okay, there's a possibility that we could be talking about something as a vector that's not one of these things. All I said was that these are examples of vectors. This doesn't completely define the concept of vector. Well, it comes pretty close, but there are other things that can be considered as vectors that don't look like just lists of numbers like that. And so, really what we say a vector is anything that satisfies these properties. Anything that satisfies these properties, and let's say this is U, V, and W are vectors, and we're not talking about where the vectors come from, we're just saying that they're vectors. And C and D belong to some number system where you can do addition, subtraction, multiplication, and division, just like the real numbers. Anything that has those properties, these properties right here, those are vectors. So we start off with simple examples like R2, R3, and slightly more complicated Rn. And we start off with these simpler ones because they're simpler. It's nice to work with something simple at first. But we're going to very slowly work our way up. All right. Now, vectors as so we've been talking about vectors as lists of numbers or arrows. And we really didn't care, are we writing them as with parentheses or angle brackets or all of these things. That was just for the sake of convenience of what we were doing in Calc 3. In this class, we're dealing with matrices, called matrix algebra for a reason. And vectors can be viewed as types of matrices. So what I'm going to do is I'm going to take, for example, the example that we've been using, 1, 2, 3, and I'm going to transform this into a matrix, an especially useful form of this vector as a matrix, which is, I'm going to transfer this to the matrix 1, 2, 3. So this is a 3 by 1 matrix. Right, I've taken a three-dimensional vector and I've represented it as a 3 by 1 or a column matrix. So this matrix consists of just one column, and that's it. And its height is equal to whatever dimension we're talking about. This will be important for our next section, which is multiplication of matrices by vectors. But for now, it's just a convention. And you just have to trust me that later on it becomes a very useful convention. Okay. How do I stop? Like, what do I do instead of saying okay? I don't know. Just don't say anything. What's next? Linear combinations. Okay, this is a fundamental importance to our class. Just like matrices and vectors are of fundamental importance, this is sort of a concept. That's of fundamental importance. The operations that we did on vectors and scalars were all the only things that we did. If this helpful, I just erased what I was going to talk about. Addition of vectors and multiplication of a vector by a scalar. We're going to combine these together, come up with a concept. And that is the concept of the linear combination. Trying to think of how I want to phrase this. Let's do it like this. I want to start with a simple definition. Linear combination of vectors. Implicitly, I'm saying these are vectors like the same dimension. I don't know if anybody had this concern that we were talking about two-dimensional vectors and three-dimensional vectors. And when I said adding vectors, I guess I did say that they're all vectors in the same vector space. But yeah, we don't have an addition defined for a two-dimensional vector to a three-dimensional vector. Implicitly, when we talk about adding vectors, we're always talking about vectors of the same dimension with the same field of coefficients, or the same field of scalars. Okay, so it's a linear combination. A linear combination of vectors is a sum of those vectors scaled. So we take each of these vectors, we scale them by some amount, we multiply some scalar by them, and then we add them all together. Symbolically, what is this? This is if V1 up to V, K are K vectors in some vector space, R2 or R3 or Rn, for some n, doesn't matter. Then A1, V1 plus A2, V2 plus dot, 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 A, K, V, K for A, R. So some real numbers, A1, A2, A3, A4 up to AK. Okay, so any choice of real numbers. This is a linear combination of those vectors. So we scaled each of these vectors by some amount and added them together, and that's a linear combination. The book calls these things weights. Call them weights or coefficients or scalars or whatever. Weights is a perfectly good term for it, I just don't hear it that often. But I should point it out that the book uses this term. Okay. Well, let's do an example. That's a perfectly good time to do an example. Does this make sense to everybody? I'm doing vectory things with vectors. Any vectory thing that I can do with vectors, what do vectors do? They add together and they multiply by scalars. So this is basically every vectory thing that I can do with vectors is a linear combination of them. That's the whole idea. What kind of vectory stuff can I make out of vectors? It's their linear combination. It's the only operations that we've defined on them. Well, I'll do an example from the book. Let's say A1 is equal to the vector 1 minus, make it a little bigger, 1 minus 2, 5.